Electrocardiography for Healthcare Professionals, Chapter 2, Cardiovascular System. Your learning outcomes. We're going to explain how circulation occurs in relationship to the ECG. Recall the structures of the heart, including the valves, chambers, and vessels. Differentiate among pulmonary, systemic, and coronary circulation, and explain the cardiac cycle, including difference between systole and diastole. Describe the parts and function of the heart and conduction system and how they relate to the ECG. And we're going to describe the heart activity that produces each part of the ECG waveform. All right, so the circulation and the ECG. Functions of the heart. The heart is to pump blood to and from all body tissues. It supplies tissues with nutrients and oxygen, and it removes carbon dioxide and waste. The circulation process is the process of transporting blood throughout the body. It depends on the electrical activity of the heart as well as the ability of the heart to contract. So without contraction, that motion, that working, the activity of the heart will produce less circulation throughout the body. So it depends on how the heart actually contracts, because remember the pumping of the heart actually helps to propel the blood throughout the body. The ECG records the heart's electrical activity. The ECG records the heart's electrical activity. All right, so what is the function of the heart? The heart's function is to pump blood to and from all body tissues. Key terms: aorta, aortic semilunar valve. Semilunar is just saying that it is half shape. The atrium, plural is atria. Caudinae tendineae. We're going to find out, or you should read those terms to know what they are. Caudinae tendineae. That is a structure inside of the heart as well. And then deoxygenated blood. We know about deoxygenated blood, and it is found in the veins. Deoxygenated blood is first returned to the heart through the atrium. Interventricular septum, that is between the two ventricles. Left atrium, left ventricle, and mitral valve or bicuspid valve. And your oxygenated blood, okay? So these are the terms which you should already know. Papillary muscles, pericardium, pulmonary artery, pulmonary semilunar valve, again, semilunar, half shape. Pulmonary veins, you know where the pulmonary veins are, going to the to the lungs, pulmonary, we know it's pulmonary, to or from the lungs via the pulmonary arteries or the veins. Right atrium, right ventricle, semilunar valve, tricuspid valve, and the vena cava. Most of these terms are already familiar to you, so make sure you know the ones. Papillary muscle is about the only one that would be considered new. All right, so the anatomy of the heart. Here you see that the heart is behind the sternum, that sternum bone, slightly to the right and to the left. Majority of it is to the left. And then we have the apex of the heart is the lower piece, as it's pointed to the apex, the very base of the heart. We have the mid-clavicular line, which is midway of your clavicle bone, your collarbone is here up at the top. This is considered your clavicle. So it's midway, the middle of the clavicle. So midclavicular line is a line that's able to pass through the middle of the clavicular bone. All right, we have intercostal spaces, meaning intercostal between the ribs. So we have a rib, 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 rib. And we have spaces that's in between the ribs, okay? And then we see the sternum here, we see the base of the heart, the apex of the heart. Okay, the base here is at the very bottom, which is going to give the maximum pulse of the heart. Some medications that the patients take, we have to do the apex heart rate. And then you see here we have the diaphragm. The diaphragm is here, okay? Diaphragm on both sides. Midclavicular and midclavicular would also be on this side as well. You see the ribs, and then the spaces between the ribs or your intercostal spaces. The heart lies in the center of the chest under the sternum, between the lungs, and it is about the size of your fist, okay? About the average size of your fist. It weighs 10.6 or 300 grams. It weighs 10.6 ounces or 300 grams. Heart statistics. Average beats. Average 72 per minute, 100,000 per day, and 22.5 billion in your lifetime. 72 average beats. You didn't say anything about the norm, the average. Average per minute is 72, average per day is 100,000, and per lifetime would be considered 22.5 billion. Your average output is 70 mLs of blood per heartbeat. So think of a little medicine cup that you may find on top of the Pepto-Bismol or any medication you might buy from the store, that 30 cc little cup that you take your medication with. If that's 30 cc's, 2 of those is 60, and then you add 10 more to it. So 70 mLs is about what the heart does, the average output per beat. It releases that much blood per beat. And the total output is 5 liters per minute. 5 liters. So you have a 1 liter or a 2 liter drink. Think of that, 5 liters per minute. 5 liters per minute. All right, 70 mLs, which is a small amount per beat, but yet within that minute, you get 2 liters and a 1 liter. Just think of those sizes, 2 liters and a 1 liter. The heart's anatomy, we have the pericardium, the pericardial space, the epicardium, myocardium, as well as the endocardium. Again, these terms are familiar to you because you follow heed. You took heed of me telling you needed to know the heart's anatomy, and it would actually help you out with the EKG portion. All right, pericardium. Around that sac, there's a space, the pericardial space between, and then we have the heart, epi, myo, and endo. Epi at the surface, myo is in the middle muscle, and endo is further within. The layers of the heart. All right, so here we have the layers. We have here, which is the endocardium. That is the part that the blood flows against. Then we have the myocardium, which is the muscle of the heart. And then we have the epicardium, which is the very top here, the very top layer. All right, we have what's called the pericardial space. And it has actually a fluid that's in there, okay? And it acts as an impact. We have a pericardium, and then we have coronary blood vessels. So you know these 3 here, okay? And this is just saying it's another name, okay? Visceral pericardium. And then we have a parietal pericardium. And we have a pericardial space. That's a space. Heart chambers, vessels, and valves. And as you know, we know of the superior vena cava, the aortic valve, right pulmonary artery, the right atrium, tricuspid valve, right ventricle, and the inferior vena cava. Now, the branches of the right pulmonary veins are here, okay? The branches of the right pulmonary veins, and we also have the pulmonary artery. So again, we know these terms: aorta, the left pulmonary artery, pulmonary trunk. That is a trunk because it goes toward both right and left lungs. We have the left pulmonary veins, the left atrium, the mitral valve, the caudinae tendineae, left ventricle, papillary muscle, and then your interventricular septum. So we see here that the caudinae tendineae, you see here, that is that material attached to the muscle. So it's like a screen door where the muscle pulls. When it's contracted, it pulls back and it actually opens up the valves. Okay, it swings open, and then when it relaxes and releases, it closes like a screen door. And so that blood should not be able to flow back in a regurgitation state, meaning it's flowing backwards. It should continue forward. All right, we have the heart. I'm going the wrong way, I'm sorry. The heart valves: tricuspid valve, mitral valve, bicuspid. Semilunar valves are your aortic and pulmonary, and we say semilunar simply because they are considered to be in a half shape. We have the pulmonary, aortic, mitral valve, and the tricuspid valve. Here you see 1, 2, 3, they call it tri, and here you see where it is 2, where we get bi. All right. Major vessels to the heart, vessels to and from the heart. Major vessels to and from the heart. Oxygenated and deoxygenated blood. This is not the first time you have seen this particular page here. We have blue for deoxygenated and red for oxygenated. I'm not going to go through this because you already know how it works. And you also know the two different circulations, pulmonary and systemic. Which valve of the heart lies between the left atrium and the left ventricle? Remember, we have to see this in an anatomical position. The left atrium and the left ventricle. All right. The mitral or the bicuspid valve. Okay, the mitral or the bicuspid valve on the left side. So therefore, on the right side, we know that would be the tricuspid valve. Name the 3 layers of the heart. Endo, myo, epi. Endocardium, myocardium, as well as the epicardium. Key terms: coronary circulation, pulmonary circulation, systemic circulation, pulmonary, coronary, and systemic circulations. Make sure you're reading the terms. Make sure you're reading the terms thoroughly. Okay, there's 3 here. Coronary circulation. All right, so if we look here, we see that we have a pulmonary circulation here. Okay, we have the lungs, capillaries, lung capillaries. Over here, we have a systemic circulation. It says to and from the body. So the circulation to the tissues of the head, and then we have circulation to the tissues of the lower body. All right, we have a top and a bottom. All right, we have tissues and capillaries here where we make that exchange, CO2 for O2, as well as here in the lower part as well. We make an exchange. CO2 is in the deoxygenated, it picks up oxygen. And so therefore it's now oxygenated blood. Pulmonary circulation is when the blood enters into the right atrium. The right atrium, pulmonary circulation, the blood passes through the tricuspid valve to the right ventricle. Blood enters the right atrium. Blood passes through the tricuspid valve to the right ventricle. The right ventricle then pumps blood into the lungs. Remember, your ventricles are your pumps, okay? Your ventricles are your pumps. And then the blood returns into the left atrium. It returns. That means it has gone already to the lungs. And when it's ready to return, that first deposit is the left atrium. Systemic circulation, the blood enters the left atrium and passes through into the left ventricle. The left ventricle pumps to the aorta. And then from the aorta, blood circulates throughout the body. So again, this is something you already know in regard to the systemic circulation. Deoxygenated blood returns to the right atrium of the heart. Coronary circulation. When we talk about the arteries, there's different arteries. Branches of the coronary arteries actually supplies blood to the heart tissue. Branches of the coronary arteries supply blood to the heart tissues. So we have a right coronary artery here. Okay, right coronary arteries, all these different arteries. And then here we have a circumflex artery. So the heart actually has arteries that supply blood to itself. Okay, the right coronary artery. Branches of the coronary artery supply blood to the heart tissues. Coronary circulation, we have the veins, which are branches of the coronary veins, drains blood from the heart tissue. Okay, so we have, once that blood has been used by the heart, then you have your veins that actually drains the blood from the heart tissue. It drains the blood from the heart tissue. We have posterior veins of the left ventricle. You have a great cardiac vein, okay? And then we have a middle cardiac vein, small cardiac veins. So again, it works in the same way. We have arteries that supplies the heart, and as well as veins that drains the heart of the deoxygenated blood. Okay, the heart as a pump, the stroke volume, we want to say that is the amount of blood ejected with each contraction. The amount of blood ejected with each contraction varies with gender, size, physical fitness, disease, as well as genetics. Your cardiac output, volume of blood pumped per minute. And we talked about that volume of blood pumped per minute. Estimated by multiplying the heart rate by stroke volume. So the heart rate, we say times the stroke volume equals your cardiac output. Your heart rate, whatever the heart rate is determined by the patient, and then the stroke volume, which is the amount of blood ejected with each contraction, equals the volume of blood pumped per minute. Which side of the heart pumps deoxygenated blood? The right side, that is correct. How is cardiac output estimated? And I just stated that. How is cardiac output estimated? Do you remember? By multiplying the heart rate by the stroke volume equals CO, cardiac output. The heart rate times the stroke volume equal the output. More key terms, your cardiac cycle, diastole, and systole. Cardiac cycle, diastole, and systole. All right, the cardiac cycle, diastole. That is heart relaxation. Diastole, heart relaxation. The relaxation of the heart. Relaxation phase, the blood returns to the heart via the superior and inferior vena cava. The blood flows from the right atrium into the right ventricle. And then the blood from the pulmonary veins flows from the left atrium into the left ventricle. And you know where the pulmonary veins are. This is during the relaxation phase. This is what's going on inside the heart during this particular phase. Systole, the heart contracts. Contraction of the heart. Contraction of the heart. This is what it looks like. Contraction creates pressure opening the pulmonary and aortic valves. Blood from the right ventricle flows to the lungs. Blood from the left ventricle flows through the aorta to the body. Systole. S over D. Contraction is creating pressure, opening up the pulmonary and aortic valves. The blood from the right ventricle flows to the lungs, and then your blood from the left ventricle flows through the aorta to the body. The relaxation phase of the cardiac cycle is known as what? Relaxation. Don't rush to answer. Correct. You said diastole. Great job. Conduction system of the heart. Okay, I gave you a beautiful heart that talks about the conduction system. So we have atrioventricular node, AV. Automaticity. Bachmann's bundle. Bundle branches. Bundle of His. AV node is another name. And conductivity. Again, make sure you're reading the definition for these terms. Contractility. Contractility. Excitability. Myocardial. Parasympathetic. Purkinje fibers. Purkinje network. Sinoatrial node, SA, and I see an AV. Sympathetic. All right, unique qualities of the heart. The heart's unique qualities initiate and control the beating. That's just what the heart does. It's unique, just like that. So where it is able to initiate and control the beating. Automaticity, conductivity, contractility, and excitability. Regulation of the heart. Autonomic nervous system, sympathetic branch secretes norepinephrine, which increases heart rate and contractility. It increases the heart rate and contractility. So if we go back, we see automaticity, which that is the ability of the heart to initiate an electrical pulse without being stimulated by another or independent source. It's automatic, just as what it sounds like, automaticity. Then we have conductivity, which is the ability of the heart cells to receive and transmit an electrical impulse. It's able to conduct under a normal cycle. And then we have contractility, the ability of the heart muscle cells to shorten in response to an electrical stimulus. It's contracting, contractility, contract. And then excitability, the ability of the heart muscle cells to respond to an impulse or stimulus, also called irritability. Okay, so now it's been stimulated, it's excited. So excitability, contractility, it's able to contract. Conductivity, let's just say, hey, it's able to receive and transmit as normal. And then automaticity, it is automatic. It does not need help from an outside source. Your parasympathetic branch, it secretes acetylcholine, and it decreases the heart rate by stimulating the vagus nerve. All right, so we have parasympathetic, the part of the ANS that helps slow the heart rate, as well as sympathetic, which is the part of the ANS that causes an increase in the heart rate. Increase and decrease, okay? Increase is sympathetic. Parasympathetic is decrease. All right, so to distinguish between the two, your P almost look like a D. If you didn't stop at that mid place and go all the way down, that P will look like a D. So associate that P as a little d and say decrease. And then sympathetic would be the opposite, which is increase, okay? That P looks like a little d up top, so it's decrease, and sympathetic is increase. Sympathetic is norepinephrine, and parasympathetic is acetylcholine, okay? Acetylcholine and norepinephrine. Acetylcholine and norepinephrine. Know which goes where. One increases the heart rate and contractility, and the other decreases the heart rate by stimulating the vagus nerve. Other factors that affect the heart rate include exercise, stress, body temperature, blood pressure, as well as electrolyte levels. All affect the heart rate. So if your electrolytes are off, imbalanced, it affects your heart rate. The pathway for conduction. Again, you have a picture where it actually starts in the SA node, sinoatrial node here in the right atrium. And then it goes down to the internodal pathway here. This is your atrioventricular node. So you have an SA node, your first pacemaker, and then your AV node, second pacemaker here. And then we go down into the right and left. We have bundle branches here. Okay, bundle branches, right and left. We have an atrioventricular bundle here that branches into the right and left. And we have Purkinje fibers that wraps around here, the Purkinje fibers. Okay, Purkinje fiber. And this would be the apex of the heart. And we have that intraventricular septum. All right, so again, knowing the heart is going to help you, look at this and be able to differentiate the locations here, but we do have that SA node and the AV node that we need to place, as well as the atrioventricular bundle. So that's the atrioventricular bundle, and it just branches off into two, which is considered to be the left bundle branch, as well as the right bundle branch. Purkinje fibers are these little finger-like projections that comes out. Purkinje fibers. And then you have the Bachmann's bundle up here, Bachmann's bundle. SA node, Bachmann's bundle. AV node, bundle of His, bundle branches, Purkinje fibers, and I discussed all those already. So the SA node and the Bachmann's bundle. The SA node located in the upper portion of the right atrium. It initiates the heartbeat. Remember, that is the initial pacemaker. So the beats there is 60 to 100. The pacemaker of the heart, 60 to 100 beats per minute. The normal conduction begins in the SA node. And the Bachmann's bundle relays the impulse from the SA node to the rest of the left atrium. So remember, when that P wave begin to form, I said it initiate in the right side of the atrium and transfer over to the left atrium. That impulse, Bachmann's bundle, it relays the impulse from the right side to the left side. Atrioventricular node. It is located on the floor of the right atrium. The floor of the right atrium. And as you look through here, you just look at the picture on page 40, and it says it's on the floor, okay? It says atrioventricular node. So kind of follow with the diagram as well, since we're no longer on the picture that was a part of the slide. All right, it causes the delay in the electrical impulse. It says, hold up, wait a minute, we need to slow down. Let's slow it down. All right, it's going to cause a delay in the electrical impulse. It can act as a pacemaker if the SA node is not working. So remember, we talked about the first one, the initial pacemaker, 60 to 100 beats per minute. So this is what we call an inherent rate of 40 to 60 beats per minute at the SA node. So that will be the second, 40 to 60 beats per minute. Okay, it's going to initiate 40 to 60 beats per minute. Your bundle of His and bundle branches. The bundle of His is located next to the AV node. All right, so just after that, you have the centerpiece that's beginning to head down the interventricular septum that is located next to the AV node. It transfers electrical impulses from the atria to the ventricles. It transfers impulses from the atria to the ventricles. So from the atrium to the ventricles, we have this location we have to first pass through, which would be considered what? The bundle of His, or we say the AV node, okay? The AV node or the bundle of His. We have bundle branches, which splits the electrical impulses down the right and left side, stimulates left and right ventricles to contract, and it stimulates interventricular septum to contract in left to right pattern. Stimulate the interventricular septum to contract to in a left to right pattern. So it's going to contract from the left side to the right side. Then we have our Purkinje network. Electrical pathway for each cardiac cell. The impulse activates left and right ventricles simultaneously. So when those Purkinje fibers are wrapped around, it's doing it at the same time. The impulse activates left and right ventricles simultaneously at the same time. Produce an electrical wave that results in contraction. Produce an electrical wave that results in contraction. All right, identify each part of the conduction system A to I, then view the next slide for the answers. So we have A, B, C, D, E, F, G, H, and I. Do you remember? Do you remember? Go ahead, I'm gonna give you time before I move on to the answers. I will give you time. All right, so you should know all of them, okay? We're going on. So here are the answers. Your A is SA node, B is AV node, C is AV bundle, D, Purkinje fibers, E, interventricular septum, F, Bachman's bundle, G, left bundle branch, H, right bundle branch, and I, apex. This might be a quiz any day. All right, what is the ability of the heart to generate an electrical impulse called? What is the heart's ability to generate an electrical impulse? Automaticity. It's going to do it regardless. It's going to do it regardless. The automaticity, it's automatic. You do not tell your heart when to beat. Which part of the conduction system is known as the pacemaker of the heart? Which part of the conduction system is known as the pacemaker of the heart? The sinoatrial or SA node. Remember, 60 to 100, make sure you know the 60 to 100 as well as the next pacemaker, all right, would be what, 40 to 60, and your last pacemaker will be 20 to 40. Make sure you know those numbers. All right, electrical stimulation and the ECG waveform. Action potential, complexes, depolarization, interval, ischemia, isoelectric, polarization, repolarization, segment, electrical stimulation, polarization, the state of cellular rest in which the inside is negatively charged and outside is positively charged. Polarization. Just see that as the resting state. The resting state. Cells are at peak resting energy. Depolarization. The electrical activation of the cells of the heart that initiates contraction of the heart muscle. State of stimulation that precedes contraction. Electrical activation of heart cells. State of stimulation that precedes contraction. Okay. Causes the heart to contract. Polarization is resting. You give that P another leg and it will be a R. So that's resting. If you want to remember it like that, I'm always giving you ways to remember, but you may already have it. Depolarization is contraction. C and D, like the alphabet. Contraction, depolarization, C and D. If that's the way that can help you. If you already know it, great. Polarization, you see that P as an R, put a leg to it for resting. Depolarization, contraction. C and D come together in the alphabet. Repolarization, state of regular cellular recovery following the contraction. Repolarization, recovery. Cells returns to a resting state. The heart relaxes, allowing for refilling of the chamber. So this is the relaxation time. This is the recovery time where the heart actually relaxes and allow for refilling of the chambers. Okay, refilling of the chambers. It returns to a resting state. It's recovering. ECG waveforms. All right, this is familiar to something you've already seen on the first day. We have the PR intervals, ST segments, QT interval, QRS complex, as well as our PQRST waveforms. This is a recorded activity of depolarization and repolarization. That is what you see, repolarization and depolarization. The isoelectric line or baseline. The isoelectric line, or what we term as a baseline, okay? Isoelectric, the period when the electrical tracing on the ECG is at 0 or a straight line. There is no positive or negative deflection. So your isoelectric line is everywhere where you see a straight. It's not going up, it's not curving, it is just straight. It's that straight, no activity is going on at that point, no activity. It is not coming up from that baseline. And then we have labeled P, Q, R, S, and T. P wave. Your P wave is the first positive deflection, okay? That's why I gave you this information the other day, even though it was kind of, I don't know what you're talking about. It's still going to help you at this point right now. Your P is your first positive deflection, and it represents atrial depolarization and atrial contraction. We said that the P begins to form in the atrium. So that's where we have atrial. Depolarization, you see the full resting and contracting of your P wave. All right. Repolarization, as well, I'm sorry, not repolarization, depolarization. It represents atrial depolarization and atrial contraction, your P wave. It is small compared to other ECG waves. Your QRS complex consists of a QRS wave. Your Q wave represents conduction of impulse down the interventricular septum. And remember, I said that wave, the conductivity is going downward. Okay, it's going downward, is beginning down the ventricles, down the interventricular septum. And then your first negative deflection occurs before the R wave. So you have a Q. That is your first negative deflection, which is your Q wave. And then it shoots up to the tallest peak, which is your R wave. Not always visualized on the ECG, so you may not always see it. The first negative deflection occurs before your R wave, which is the Q, and it's not always visualized on the ECG. It is less than 1/4 the height of the R wave. Less than 1/4. So your R wave, cut it in 4, and your Q wave is typically going to be 1/4 of that. 1/4 of the height of your R wave. Your QRS complex, your R wave, the first positive wave of the QRS complex because it's going up above the isoelectric line. And it represents conduction of electrical impulses to the left ventricle. It represents conduction of electrical impulses to the left ventricle. This is the first positive wave of the QRS complex, which is your R, and it represents conduction of electrical impulse to your left ventricle, your R wave. Your R wave. Your S wave, the first negative deflection after the R wave. It represents conduction of electrical impulse through both ventricles. So your R wave is just the left ventricle. Your S wave is both ventricles. Okay? Your left ventricle is your R wave, and your S wave is the impulse through both ventricles, both. Think of simultaneously when you think of your S wave, because at one point it said that it stimulates simultaneously. So think of the S as simultaneously to say both, both. And then you're right, your R wave begins R wave is your left ventricle. Your ST segment, it measured from the end of the S wave to the beginning of the T wave. And if you need to use look in your book on 44, measured from the end of the S wave to the beginning of the T wave, indicates end of ventricular depolarization and beginning of ventricular repolarization. All right, so if we look at that ST on 44, it says it indicates the end of ventricular depolarization and it begins ventricular repolarization. That's the ST segment. And it's normally on the isoelectric line, your segment. You see it is on the line. Elevation or depression of your ST segment may result from ischemia. Ischemia is that period of lack of oxygen. If it's elevated above the line or depressed below the line, it may be due to ischemia. Your T wave. Your T wave represents ventricular repolarization. The normal T wave is in the same direction as your R wave and the P wave. It's a positive reflection. And it represents ventricular repolarization. Repolarization, ventricular repolarization. Ventricular repolarization. All right, so if you look at page 42, these tables are very excellent in this textbook. So if you look at the table, it has what we just discussed, the P wave, upright, small curve, atrial depolarization with resulting atrial contraction. So look at this table. It tells you the component of the wave, the appearance and what it should look like, as well as what is going on with the heart at that time. Make sure you look at that table. On page 42, table 2.4, ECG components. Please look at that. Your U wave follows the T wave. It represents repolarization of the bundle of His and the Purkinje fibers, and it's not seen on all ECGs. You're not going to be guaranteed to see a U wave. That is not normal to find it on a normal ECG, but it may happen. So it's saying you may not see it on all of them, so don't look for them. The presence can indicate an electrolyte imbalance. So if there's electrolyte imbalance going on, then you may see it. Your PR interval is measured from beginning of P wave to the beginning of your QRS complex. Normal length of time is 0.2 to 0.2 seconds. Interval should be consistent. It should be consistent throughout the waveforms, throughout the reading. Your QR interval, the time required for ventricular depolarization and repolarization to occur. That is the time required for ventricular depolarization and repolarization to occur. So within that time frame, ventricular depolarization and repolarization should be taking place. And it starts at beginning of QRS complex and ends at the end of the T wave. Includes your QRS complex, ST segment, and T wave. Normally measures less than 1/2 of RR interval. Normally measures less than 1/2 of the RR interval. Your RR interval is the time from the start of one QRS complex to the start of the next QRS complex, from start to the next. So that RR interval, and I showed you yesterday, if you put your paper on the two highest peaks, that RR, okay, that is the time it takes between one QRS and the next. And we actually can use this to calculate the heart rate. Your J point, the junction of the QRS interval and the ST interval. All right, it's a junction where your QRS interval and your ST interval, that's a junction between the two. It represents the end of your QRS complex and ventricular depolarization. It represents the end of the QRS complex and ventricular depolarization. Important when measuring the length of the QRS complex. It is important in measuring the length of the QRS complex. Which wave of the ECG waveform represents ventricular repolarization? Again, the table on 4.2, table 2.4, ECG components, make sure you read and know the heart's activity at the time of these waveforms. On the sheets that I've already given you, yes, it may just have the alphabets there, but go ahead and include what's inside this table on one of those sheets as well, okay? Go ahead and include what's in the table on page 42 beside the letters that's on one of your pages. You have multiple pages. You can include it on either one of them. Your T wave, and it says that here, your T wave is ventricular repolarization. Don't get scared. Just look at it. It's simple. Read it. Read it and memorize it. What is the normal length of time for the PR interval? The normal length of time for your PR interval. 0.2 to 0.2 seconds, yes. Your chapter summary. The function of the heart is to pump blood to and from all body tissues. The heart has 3 layers and is covered by the pericardium. The heart consists of 4 chambers and 4 valves. The coronary arteries supply oxygenated blood to the heart, and the coronary veins remove carbon dioxide and waste. Blood travels or circulates through 3 pathways, either pulmonary, systemic, or coronary. The cardiac cycle consists of a contraction phase and a relaxation phase, which is systole and diastole. The conduction system of the heart generates and maintains electrical activity. Unique qualities of the heart cells include automaticity, conductivity, contractility, and excitability. Know the difference between those. The systemic and parasympathetic branches of the autonomic nervous system regulates the heart. And remember, systemic and parasympathetic, they release these chemicals that you need to know. Systemic and parasympathetic, which increases the heart, which takes place when it's decreased. Which one? Parasympathetic. Put your relationship between them so that you can know. The heart's conduction system includes the SA node, AV node, the bundle of His, bundle branches, and Purkinje fibers. Get familiar with those. Depolarization causes the heart to contract, and repolarization allows the cells to recover. The ECG waveform is created by the various activities of the conduction system. The ECG waveform includes the P wave, QRS complex, T wave, U wave, PR interval, QT interval, as well as the ST segment.